I hope my slide is visible.
Yes, sir.
Okay, so from today we'll start with the new topic. We'll discuss about the compressor and the expansion device. So the two groups which have already attended the lab class would be aware with the introduction to the compressor, and very briefly we have seen a device called the thermostatic expansion device. So now in this module, we'll discuss mainly about reciprocating compressor, because those compressors are easier to uh, study in a classroom environment. But you already know that there are other types of compressors. And in the expansion device, we'll look at the capillary tube, how to size the capillary tube, okay, and the principle of operation of thermostatic expansion valve, and how it manages with variable load condition. And we'll briefly look at something called the electronic expansion valve also. But there's not a lot to discuss in the EEV, because once we understand the TEV, you will see that EEV is just programming the features of the mechanical valve. So we'll start off with the compressors. So the two sections which have already attended the RSC lab classes, they'll be aware of with all the different types of compressors which we have discussed. And the next batch, which is going to come from, I think, the next week onwards, they'll also get to know the various types of compressors. So for the time being, I'll skip this. What we are going to study in this theory class is only about the reciprocating compressor. Okay, but as I've already told you, that the features of a reciprocating compressor and features of other positive displacement type compressor, be it a rolling piston scroll or a screw type, the principle remains same. The thermodynamic analysis is also very similar. It is just that the geometries are complicated here, and hence we cannot simply write the expressions without doing a thorough simulation or a thorough experimental study. So that makes it difficult to study all these things in a classroom environment. But whatever we are going to discuss today in our reciprocating compressor class, uh, you can broadly take it as the theory even for the rolling piston scroll and screw type. It is only the fluid dynamics part which will vary. So if I were to simulate the flow pattern inside a reciprocating compressor during the suction and then the compression and then the discharge phase, the entire fluid dynamics would be different from a rolling piston or a scroll or a screw type. Okay. And the rotodynamic compressors and turbines will be discussed in the next ATF class, that is ATF2 in next semester. So this entire topic we are going to skip for this uh, course. Okay, so when you discuss about the power plants, you will also learn about the turbines and various types of turbines, and the same mathematical principles are valid for a compressor also. So this is a very elaborate, this requires a very elaborate analysis and discussion and introduction to new concepts. So that's why this is not going to feature in our study, neither in the lab class also. Whereas in the lab class, we'll discuss about these three type of compressors. We in fact have one uh, compressor of the rolling piston type. Okay, we do not have a scroll or a screw. They are huge. Scroll is not very huge, but screw compressors are typically very huge. So, but we'll see some animations, people who have not yet attended the RAC class. So what we are going to focus in this theoretical aspect of reciprocating compressor is mainly the performance aspect. Okay, the performance of a reciprocating compressor. Now, what we are looking at when we call as performance of a reciprocating compressor is, of course, what is the mass flow rate it can deliver, okay, for a given displacement volume. Then what is the power consumption? Very important. Okay. It should be W dot. And temperature of the refrigerant at the compressor exit. Okay, so this is not independent of the power consumption and the operating conditions. Uh, so you will see that the geometry of the compressor and the amount of clearance volume, those things, they'll decide what is the mass flow rate it can deliver. Whereas the operating conditions will decide these two parameters. Of course, operating condition also affects this for a particular geometry. Okay, and then what is the type of compressor? What is the isentropic efficiency? All those things will go into this work of compression part. So reciprocating compressors are typically have slightly more losses compared to, say, a rolling piston. So most of the modern ACs will come with the rolling piston type compressor. Unless it's a very cheap one, you can get a 1-ton AC costing you 20,000 all the way to 35,000 or even more. Okay, so the cost also decides which type of compressor you will have. So slowly the industry standard is shifting now from the reciprocating to rolling piston type compressor for the residential ACs. In the domestic refrigerators, you will still find a lot of reciprocating compressors, but even there also we are slowly shifting to the rolling piston type. So the type of compressor will also decide what is the losses. But since we are just focusing on the reciprocating compressor, so we'll restrict all our discussions to this. Now, the most important aspect when you discuss about a compressor is what is the mass flow rate it will deliver. Okay. And this is what is very important while sizing any system. So let's say you are supposed to, so nobody nowadays designs an entire AC because you get all the components from various vendors. So what you just eventually need to do is you have to size. So if you are tasked with sizing a refrigeration system for a cold storage facility or let's say air conditioning facility for a theater. So you will not go about designing the compressor and uh, fabricating a new compressor. No. So you will just look for what are the compressors which are available in the market. Okay, what is the load that you expect, and you will try to match those things. So that's what I meant by sizing. So you may have a compressor of a particular displacement volume. Okay, and now you will have to decide if this much displacement is enough for my application. Similarly, when you have to design the evaporator, you will again look for some standard heat exchangers which are available in the market. In case they are not, then you will go for designing a customized heat exchanger. So you will also size your evaporator, you will also size your condenser, and you will also size your expansion valve. Okay, so again over here you will have manufacturer data sheets. You will not have expansion valve which cater to let's say you have a 1-ton AC, then you have 1.5-ton AC. So if you go into the market and look for compressors and expansion devices, you will be able to get them for these tonnage. You will not get it for 1.2 ton. Okay, there are some ACs which are available, but it's very rare. So similarly, when you are sizing or designing a refrigeration system, you will find these difficulties. Okay, be it your compressor, be it your expansion valve. So based on your application, you will have to decide. So as a design engineer, you'll have to decide which component to be chosen. So when it comes to compressor, the most important thing is the mass flow rate of refrigerant it will deliver. Now what it depends on? It depends on, of course, the displacement volume and something called the volumetric efficiency. So have you learnt about volumetric efficiency in your IC engines class?
Yes, sir.
So why it is necessary over there in an IC engine? Why it is very important to understand this term called volumetric efficiency? What does it affect? Can anyone tell me why do we need to study volumetric efficiency in IC engines? Okay, what do you know about volumetric efficiency? Whatever you have studied in IC engine, what do you know about it? What is the definition?
So it is the total cylinder volume divided by the clearance volume.
Total cylinder volume. So I can call it as total cylinder volume. Okay, V displacement plus the clearance divided by the clearance volume. So this number will be greater than 1. No? Clearance volumes are typically very small. This is the total volume. Or is it the reverse?
Inverse of this.
Okay, inverse of this will give me something called as clearance ratio. No? This is something called as clearance ratio. Is volumetric efficiency a fixed number?
The amount of air and fuel mixture entering depends on the pressure difference. So all the air cannot enter. So the actual air divided by the theoretical amount is the volumetric.
Yes, great. So that is not a fixed number, as you said. So it depends on the operating condition. So it depends on the pressure ratios. Okay, so same is the case with a reciprocating compressor. Okay, so in my lab class, as I have told you that why we see so many reciprocating compressors in our day-to-day life is because it's a very mature technology, and we have a parallel technology, that is the IC engines, which has progressed a lot, and we have taken all our knowledge and understanding from there and improved the reciprocating compressors. Whereas if you look at other technologies, especially the rolling piston scroll, it took more time for us to, from the point of identifying that yes, this is a better, a more efficient compressor, till the point we actually built commercial systems, that it took more time, because that is specific now to the refrigeration industry. So the terminologies that we are going to discuss in the reciprocating compressor, you may find parallel analogous terminologies in the IC engine subject also. So over here, volumetric efficiency is defined as your friend said, that whatever the actual refrigerant which is entering divided by the theoretical that will enter. Okay, so let's look at the entire compression process in a ideal reciprocating compressor. It is very similar to what you have discussed already in the IC engine. Okay, so let's say you start off at this position. So this is your piston cylinder assembly. Okay, this is your top dead center, and this is the bottom dead center. Now at the top dead center, you will still have some clearance volume. Okay, it will not go and hit these valves. Okay, so this is the intake and this is the discharge. So the intake valve will displace inwards, whereas the discharge valve will displace outwards. Okay, and students, first two batches have already seen how these valves look. So they are basically just thin rings or plates, very thin. and they simply flex based on the pressure difference between these two ends. So if you have a higher pressure over here and a lower pressure over here, it will automatically bend inwards. Similarly, for the discharge valve to open, if you have a higher pressure over here and a lower pressure over here, it will move up. But then it should not open at any given moment. So we have the spring force and the backing plate and everything. So backing plate restricts the amplitude of this valve. And then you have a spring force to overcome. So the last batch, which is yet to come to the RAC class, they'll see in the next week how these valves look like. For the time being, let's schematically represent them by these two simple flaps. So this is the suction valve and this is the discharge valve. So this is the intake side of the compressor. This is the discharge side of the compressor. This is the top dead center. This is the bottom dead center. Now the same thing is represented on this PV chart. This is PV. So let's say this is my initial position where the piston is over here. I have some VC. Okay, so this VC, which is the clearance volume. Now, from this position, so you have some gas which is already trapped here, which you are not able to push out. This gas will never be pushed out. Okay, and initially the pressure, I am assuming it to be condensing pressure. It will be slightly higher than the condensing pressure. So this is the end of the discharge. Now this gas, when you have the piston moving downwards, so in this case it is towards the right. So this gas will re-expand in the piston cylinder assembly. Okay, now it will re-expand and hence the pressure inside this cylinder will go down. It will go down till you have your evaporator pressure. Okay, now any further reduction in pressure inside the cylinder will open this suction valve. So at the end of the discharge phase, this is your condition of the valve. Both the valves are right now closed and your piston is moving right. In actual sense, if you look at it vertically, then it is moving from top dead center towards the bottom dead center. So pressure goes down, and hence pressure inside this volume goes below your condensing pressure. Okay, this flap will close actually immediately, and this will not open, this intake valve or suction valve will not open till you have sufficiently low pressure inside the cylinder. Okay, and what is that sufficiently low pressure is? Just below your evaporator pressure, because here it is connected to the evaporator, here it is connected to the condenser. Now let's say at some intermediate location D, you have your pressure inside the cylinder going or reaching P evaporator. That is the time or location where the suction valve will open. So that means this flap will now move to this. Okay, definitely will not happen instantaneously, and it will not happen exactly at P evaporator. It will happen at slightly at a lower pressure because it has to overcome the spring force over here. So now at this condition, so we are just looking at the ideal condition. So at just exactly equal to P evaporator, the suction valve opens. And if you further move this piston towards the BDC, okay, what you will do is you will suck in more vapor. Pressure will not change. So it becomes an isobaric process now. So this suction is happening at location, starts at location D and continues to happen all the way till the bottom dead center. Now at this condition, now the piston will start moving up. As soon as it moves up, the pressure inside will go above your P evaporator and hence your suction valve will close. So this flap will be pushed up. Whereas the pressure inside is still not sufficient enough to open the discharge valve because it has not gone up to P condenser. So now you will have gas which is trapped inside your cylinder volume, and you have your piston moving towards your top dead center. So volume is reducing, and hence this is the time when you will have the compression. And this will happen all the way till this condition B, so which is again some intermediate volume, okay, where your pressure inside the cylinder goes up to P condenser. Now any further compression will actually lead to pressure going slightly above P condenser, and hence it will open this discharge valve. So this flap will move up and the gas inside will escape and it will go to your condenser. Okay, so now when this flap will open, this discharge valve will open, depends on what is the back pressure given by the condenser. Okay, so if you have higher condensing pressure, so this compression process will happen all the way till this position. Then if you have a lower condensing pressure, so the compression will happen only up to this location. So up to what point the compression process will happen, it depends on the back pressure which is given by the condenser. Okay, and the condenser back pressure indirectly then depends on the heat exchanger area and the ambient temperature. So P condenser depends on the area and the T ambient. Okay, definitely if you have a higher ambient temperature, it will lead to higher condensing temperatures and hence condensing pressures, and hence the back pressure on this valve will be higher. So your compressor will have to compress to a location much closer to your top dead center. Okay, but even for the same ambient temperature, if you have a heat exchanger area which is small and if you have another heat exchanger which has a higher area, you will have varying condensing temperatures, which we have discussed in the previous class. So how the internal and external regimes are connected by the heat exchanger. So I told you a 3-star AC will have a smaller area and hence it will operate at a higher condensing temperature and a lower evaporator temperature. Okay, so both these are important, and the P condenser will be dependent on both these factors. Okay, so for the time being, let's ease our discussion. So let's say you have infinite area. So your condensing temperatures are equal to your ambient temperature. Okay, so it will not change unless and until your ambient temperature changes. So based on the ambient temperature, you will have your condensing temperature, and based on that, you will have your back pressure onto this valve. And that will decide when this valve opens. So there is no one sitting over here or no instrumentation telling that the valve should open at this moment or it should not open at this moment. It is purely based on the differential pressure between the cylinder and the pressure in this line. Similarly, if you look at the suction side also, there is no one telling this valve that you have to open at this. We do not have any active control of the valve, unlike your IC engines where we have cams and other active devices to operate the valves. Okay, here it is purely based on the differential pressure. So the moment the cylinder pressure goes below your evaporator pressure, then you will have the valve opening and suction happening. And the moment you have your cylinder pressure going above your condensing pressures, you will have your discharge valve opening and discharge process happening. Okay. So if we go back to this condition B, where the pressure is just equal to P condenser, so any further compression, you will not have further overpressure. You will have just the discharge, which will start. So it will not go up. So this is again ideal discussions. So definitely we'll have to go to a pressure slightly above the P condenser because we'll have to again overcome the spring forces on the valve. So in an ideal case, as soon as the pressure is slightly above P condenser, you will have your discharge. Now discharge process will happen all the way till this position. Okay, that is your top dead center. And again, after that, you will have your piston moving back towards the bottom dead center. The pressure inside the cylinder goes below your condensing pressure. The discharge valve will close. The intake valve will still not be open because the pressure inside is higher than the evaporator. So again, it becomes a closed system. Okay, and you will have your re-expansion of the gas which is trapped in the clearance volume. Any questions?
Yep.
Yes.
Yeah, so the discharge valve will close right after the piston reaches the top dead center or just below?
So as soon as it reaches, so this is like a limiting case. So as soon as it reaches the top dead center, it will still be discharging, and then just when the velocity reverses or the direction of the piston reverses, then it will close. This is just a limiting case.
Yeah, so from top dead center to the point D, the system is completely isolated. No valve is open.
No valve is open.
Okay, after D, the suction valve opens
Yes.
while it is going to the bottom dead center.
Yes.
Yeah, thank you.
So C to D, no mass intake. Okay. And A to B also no mass intake or exit. Okay, so no mass intake or exit during this period, no mass intake or exit during this period. So it becomes a closed system. Okay. You have suction happening. Yes.
The pressures from A to B, the pressure, why doesn't the refrigerant move out through the P evaporator valve?
Through the evaporator. This one?
Yes, sir.
Okay. So have you attended the lab class? So the answer to that lies in how the valves are made. Have you attended the lab class?
Sir.
Okay. So you have attended or not attended?
Attended. Yes.
Attended. Okay. So if you just remember that the valve plate, let's say these are the two holes for the suction. In the valve plate, where was the valve located? So this is the plate in which you have hole, and let's say this is the hole for the suction. Where was the valve located? This is the direction in which gas will enter. Will the flap be located on top or at the bottom? It is
On the
bottom
top.
being this one. So then how will it open? So if you have the flap on top and gas has to enter from top to bottom, the flap will close now if it has to enter. By this force of the fluid entering, it will close the valve. So the flap is placed at the bottom, no?
Yes,
You
sir.
remember?
Understood.
So this flap is placed at the bottom. So that's why the gas pushes this flap and then enters like this. Okay, and then when the pressure inside goes higher, the gas will tend to then close this flap, isn't it? So the flap will close. Disregarding any leaks and all which may happen. Okay, if you have the continuous operation of compressor, this is one of the issue that most of the compressors will have. That's why we have open compressors where we can change the valves. This is a common failure. But if you disregard the failure of the valve where it doesn't close properly, okay, just disregard that. But ideal case, when the pressure inside the cylinder goes higher, this flap will then close just by how the flaps are placed. Does that answer your question?
Yes, sir.
Anything else?
Sir?
Yes.
So during the suction, doesn't P evaporator decrease?
During the suction, doesn't the P evaporator decrease? Okay, that's
like
a
as the suction takes place.
okay. Okay. Very good question. I understood. So now it depends on how. So that's why the sizing is important. Let's say your evaporator is sized for providing 3.5 kilowatt, which is 1 arton of cooling. It means that you will have boiling proportional to that particular amount of heat absorption inside the evaporator. So you have that much amount of vapor generation inside the evaporator. So some m dot ref is being generated inside the evaporator, and that has to be sucked by the compressor. Now suppose you attach a compressor which can deliver significantly higher mass flow rate than what you are generating inside the evaporator, then the issue, what you are telling, will happen. So your evaporator pressures will go low because you have attached a very large compressor to a small evaporator. Okay, so if you have properly sized, so that's why I was talking about sizing. So if you have properly sized the compressor, it will lead to a close to steady state, steady flow process.
Got it, sir. Thank you.
Yeah. Okay. Anything else? Okay. So now, one thing we must understand from this discussion on the entire compression process inside a reciprocating compressor is the mass gets sucked into the compressor only at this location D. Okay, even though the swept volume is VA minus VC, but the volume during which the suction process happens is starting from VD all the way till VA. Okay, and where it will happen is also not exactly in our hand for a given clearance ratio. Now, what is clearance ratio? Clearance ratio is nothing but this clearance volume divided by the displacement volume of the compressor. So this all manufacturer will provide in their data sheet. And some typical values are 1 to 2%. Normally they'll keep it below 3%. Okay, and why they have to provide? First of all, you have to accommodate the valve because this suction valve will open inwards. It requires some displacement, so some volume it will take away. Second is we'll have to take care of the thermal expansion of the piston cylinder. So we provide some additional clearance for that. Machining tolerance. Okay, this is getting better and better day by day. So you will have machining tolerance being one of the dominating factors if you pick up a compressor from 1900s because they could not machine it properly. Okay, now we can machine them very close to whatever values we require. So machining tolerance, this part is improving. Now we are limited by the volume required to accommodate the valves and of course thermal expansion. Thermal expansion is again, once you choose a material, it is not in our hand. Okay, so these two factors are dominating, and there is another fourth factor which is not mentioned. Many a times the compressor manufacturer takes into account some amount of liquid refrigerant tolerance inside the compressor. So they'll allow some small amount of liquid refrigerant entering. So with that small amount also, the compressor will not break down. Okay, so if you go to a zero clearance, then you cannot accommodate even a small fraction of liquid because when it goes towards the top dead center, you will not be able to compress the volume of liquid. Okay, the pressures will shoot up, and then it will not only try to come out of the valves, be it the suction or the discharge valve, it will also come out of the ceilings over here. Okay. So you have those piston rings. It will try to come out from here also. It will rupture the rings also. So zero clearance volume is not possible. So even if we were able to have a material which never expands on thermally, okay, and let's say we come up with an hypothetical valve which requires minimal movement to provide the suction, still we will not go for a zero clearance volume. Just to safeguard our compressor, in case there is some small amount of liquid entry into the compressor, we will want to operate safely with that. So once the clearance volume is fixed by the compressor manufacturer, then he can also tell what is the safe amount of liquid entry which this compressor can tolerate. Okay. So we cannot escape this evil, that is the clearance volume. Now why I'm calling this evil is because this vapor which was present inside after your compression process, which could not be discharged, is what is killing your suction volume. Because this volume of gas which is trapped is getting re-expanded. Okay. And it is occupying the internal volume and it is maintaining a pressure which is higher than the PE evaporator. So whatever volume of gas which is trapped, that volume of gas now has to go to a pressure below your PE evaporator so that it can accommodate additional volume from the evaporator. Okay, so from this point of view, a compressor manufacturer will want to have zero clearance volume, but then there are other practical aspects as I discussed. So most of the commercial systems will have a clearance volume typically in 1 to 2% of the displacement volume. Questions? Okay. So, so how the volumetric efficiencies are defined in case of a reciprocating compressor is the actual volume of refrigerant which is entering, okay, actual volume divided by the theoretical volume. Theoretical volume is this. Okay, again, this is not a fixed number. We will see eventually how it varies. Because this point D itself is not fixed. Even for a compressor with a fixed clearance volume, this point D is not fixed. Okay, so this is the definition VA minus VD upon VA minus VC. And then you can manipulate by adding and subtracting VC in the numerator. Okay, and then you come up with this expression. Okay, just by some simple mathematical substitution, you will end up with this expression finally. Okay, so at clearance volume divided by the displacement volume is the clearance ratio, which is given by epsilon over here. And you substitute the value for your VA over here, and then you get rid of VA. Finally, you have an expression in terms of VD, VC, and epsilon. Okay, now why we have converted this expression into VD and VC is we'll now apply one assumption over here. The assumption over here is the compression and the re-expansion. So let me write this re-expansion. And this is the compression. So this is the re-expansion, this is the compression. This is the discharge. And this is the intake. Okay, so these are the four processes which are happening. Now we'll assume, just for simplicity, that the re-expansion and the compression processes are isentropic. Okay, so that we can now simplify this expression. Or if you want to be slightly more realistic, you can consider it to be a polytropic process. Okay, so here I have given gamma, you can replace the gamma with some n. So where n is the PV to the power n constant. So this n is for the polytropic constant. Okay, so with this assumption, now what I can do is I can write this Vd over Vc in terms of the pressure ratio and either the gamma or n, whatever you want. If you assume it to be an isentropic process, so then you can write PV to the power gamma constant. If you assume it to be a polytropic process, you assume PV to the power n constant. So our idea is to just simplify this expression into this. So pressure at C is PC, P condenser, and pressure at D is P evaporator. Okay, so pressure ratio is PC over PE greater than 1. Okay, so finally what we get is a expression which involves your clearance ratio, your pressure ratio, and of course some information about the process. Okay, so now from here you can realize that your volumetric efficiency, because of the presence of the clearance volume, so that's why two subscripts are provided. So volumetric efficiency because of the presence of clearance volume. Okay, it of course not only depends on what is the clearance ratio, this is a fixed geometrical parameter. So once the compressor is manufactured, this epsilon will not change. But it also depends on the pressure ratio and it also depends on the gamma value or the n value. Okay, so it depends on the process itself and depends on the pressure ratio. Now, the beauty of writing that previous expression is now we can generate some plots from where we can make important deductions. Okay, so what will happen if I increase the pressure ratio? Or what will happen if the gamma changes? So gamma changing means changing the refrigerant. I use one refrigerant, I use another refrigerant in the same compressor. So that means that the gas properties are changing and hence the gas gamma will also change. Okay, so I can make use of this expression to draw very simplistic plots. Of course, please remember that there is still one assumption, that is ideal reciprocating compressor. Okay, but we can make some qualitative deductions from here. So if I increase the pressure ratio, the volumetric efficiencies will continue to decrease. So only if I have Rp equals to 1 will my volumetric efficiency go to 100%. Okay. Whereas if I have Rp equals to some Rp max at some maximum PC over PE, what I say is my volumetric efficiency can go to 0. It means that the compressor will not suck in or compress and discharge any mass flow rate of refrigerant at that particular Rp max. Okay, so why this is happening? Again, if we draw the entire cycle. Okay, so this is your P condenser, this is your P evaporator. Okay, this is your clearance volume. So this is your CDAP based on the previous slide nomenclature. Now, this PC over PE is your pressure ratio. Let's say maintain same PE, I increase the PC. So what will happen is now I will have to compress all the way till here. Let's say this is your new PC. I will have to compress all the way till here. Okay, I will discharge up to this volume. and I will then re-expand. Okay, so this will be my new cycle. So let me use another color. So I will have to compress all the way till here. I will discharge till this VC, and then this becomes my new cycle. Okay, if I further increase the pressure, you can now realize that I may reach a condition where this cycle having 4 processes becomes a single curve. Okay, now I reach up to this pressure PC, where after compression IC, I have to reach all the way till the top dead center. Okay, over here, I still had some room for discharge. Here, even if I reach till top dead center, I barely reach my condensing pressure. And from there, again, my piston will move down towards the bottom dead center. So whatever gas was there trapped, it gets re-expanded. Okay, it gets re-expanded. And by the time I reach my bottom dead center, my pressure goes to P evaporator. So my valves will never open, neither the discharge valve nor the suction valve in this limiting case. Okay, so this is one way, or the other way, you can keep the PC constant and reduce the PE. Same effect you can create. Okay, so the moot point is there is one RP max which your compressor can work. Beyond this pressure ratio, okay, so this is a limiting case, RP max, your mass flow rate delivered by the compressor goes to 0. Because neither the suction valve will open nor the discharge valve will open. So it will just compress the gas which is trapped in the clearance volume and re-expand, compress and re-expand. So no additional vapor being sucked in from the evaporator, no vapor being discharged to the condenser. So that is that particular maximum pressure ratio. Okay, and what it depends on, definitely your clearance ratio, okay, and your gamma, or if it is a polytropic process, then what is that polytropic constant N. Questions? Now, what is the mass flow rate which is delivered by the compressor? Okay, it is theoretically it should be given by rho evaporator. So if this is your compressor, so this is your suction valve, this is your discharge valve. So whatever the density of this vapor is at the evaporator condition, okay, into the displacement volume. That should be the mass flow rate delivered by a theoretical compressor. But now we have introduced the concept of volumetric efficiency. So your entire displacement volume is not used for sucking in the vapor. It will be multiplied by the volumetric efficiency. Okay. And of course, the numbers of cycles per second. Okay, and if you have multiple cylinders, then you can multiply that also. Okay, so if you have multiple cylinder and not just single cylinder, then you multiply this number with the n cylinders. So this will be your mass flow rate sucked in by the compressor. And that is the mass flow rate delivered by the compressor to the condenser side. Okay. Any question in this expression? No. So what is that RP max? It is just equating this volumetric efficiency to 0, rearrange the expression, and you will get that RP at which you will get volumetric efficiency 0, and you will see it is just an expression in terms of epsilon and gamma. So when you see your ACs, you will see some sticker. It can operate at 52 degrees C ambient condition. Okay, or it can operate at 60 degrees C ambient condition. So what they are mentioning indirectly is this is the maximum pressure ratio. So that information they are trying to convey that this compressor, the compressor used in this refrigeration system can deliver mass flow rate up to that maximum pressure ratio. And instead of giving you the pressure, because if I give you pressures in terms of bars and all, layman people will not understand. So instead of that, they're trying to convey some information about the condensing temperature. So even when the ambient is at 52, okay, so if there is 5 or 6 degree delta T between the ambient and the condenser, it will maybe operate at 58 to 60. Okay, so I'm assuming some numbers, so it will depend on what is the area of the condenser available. Based on this, you will have the condensing pressure, which will depend, of course, on the refrigerant being used, divided by the evaporator pressure. Okay, the worst evaporator pressure would be corresponding to 16 degree. So your ACs will go as low as 16 degree if you try to set it by the remote. So that would be the maximum or worst scenario for the compressor. It will just deliver some mass flow rate at this condition. Okay, definitely we're not going to see 52, maybe for another decade. I don't know what's the situation with the global warming, how quickly we'll reach such high temperatures in summer. But as of now, most of the ACs you will see, they'll be rated to ambient temperature of 52. Any question? Okay. So now we will come to the effect of operating conditions. Now we have seen that it depends on the operating condition, how the compressor will, how much flow rate it will deliver. Okay. Now what we will try to analyze is based on our understanding of volumetric efficiency, we will try to now vary the evaporator and condensing temperature. Okay, and try to understand how the refrigeration capacity will change and how the work consumed by the compressor will change. Because as a customer, I would only worry about these two things. बिजली कितना लेता है और ठंडा कितना करेगा. Okay, so ठंडा कितना करेगा is nothing but the refrigeration capacity. Okay, so 3 kilowatt, 4 kilowatt, 5 kilowatt, that is the capacity. And capacity is nothing but m dot refrigerant into your refrigeration effect. And refrigeration effect was, okay, so these are all pressure enthalpy charts. If you look at your TS chart also. So whatever enthalpy difference happens across your evaporator. So this is after your expansion. So this difference in enthalpy, that is inlet to the exit of the evaporator, that difference is called the refrigeration effect. Okay, so when we draw a thermodynamic cycle, we do not get the information about the mass flow rate. So that is an additional information we require. Now with our understanding of the reciprocating compressor characteristic, we will now try to relate mass flow rate also to the operating condition. Definitely refrigeration effect will depend on the operating condition because the cycles, the area under the curve and everything will change. Okay, and it is the multiplication of this m dot ref and refrigeration effect which will give us the refrigeration capacity. Because we don't care when we are operating our AC, what is the cycle, what is the thermodynamic cycle. If you are using R22, if you're using R32, you will have different enthalpy changes across the evaporator. We don't care. Okay, I can have two split ACs using two different refrigerant, yet giving same refrigeration capacity. Okay, so ultimately as an end user, I just need refrigeration capacity as the information. I need the power consumed by the compressor. So again, power consumed by the compressor is m dot ref into the enthalpy difference across the compressor. So you see that this information was missing if we were just looking at the thermodynamic cycle. So we had to bring in our understanding of the volumetric efficiency of the compressor and what is the mass flow rate that will be delivered by the compressor, and then only we can now fully see the picture. So what we will now do is we'll in one case we'll keep the condensing temperature constant and we'll vary the evaporator temperature, and in another case we'll keep the evaporator temperature constant and we'll vary the condensing temperature. In reality, both will vary based on the operating condition. So again, students who have already attended the lab classes will know, especially the second group which has attended the RAC class yesterday only. They'll see that if you change anything on the load side, the entire operating condition on the refrigerant side changes, and hence everything changes. All the pressure, temperature, everything changes. So if I keep the condensing temperature constant and vary the evaporator temperature. So these are all pressure enthalpy charts. Just be careful with that. Okay. So what will happen is we are assuming standard saturated single stage. Okay, so we have saturated condition here. We have saturated condition here. We're not bringing in the additional complexity of subcooling and superheating right now. So if I keep on reducing my evaporator temperature, what I see is this delta H across the evaporator also reduces. So this is your delta H for the first case. Okay, so this entire thing. Then the second case it got reduced to this. Third case it got reduced to this. Okay, so if you lower down your evaporator temperature, so this delta H, which is nothing but the refrigeration effect. Okay, so this is the industry used term. In the industry, they do not use delta H across evaporator, such terminology. They simply use refrigeration effect. That is the capacity divided by mass flow rate per unit mass. Keeps on reducing. Okay, so if you go to very low evaporator temperatures, your capacities will be very low. That's why your domestic refrigerators, they have very poor capacities, because they have to maintain an evaporator temperature of -25, -30, so that your ice cream remains at -18 or -20. It doesn't melt. So for such low evaporator temperatures, you will have very small refrigeration effect. Now, vice versa, if you maintain your evaporator temperature constant and your condensing temperature keeps on increasing, okay, which means that your condensing pressures are increasing, okay, you will see similar effect happening on the evaporator side again. Because see, these vertical lines are isenthalpic lines over there. So you will expand from here. In this case, you will expand from here. In a lower condensing temperature, you will expand from here. So as your condensing temperature lowers, you will have higher refrigeration effect. As your condensing temperature goes higher, your refrigeration effect will reduce. Okay, so that's why if you use your AC or your refrigerator during summer and the same AC during winter, you will expect more RE, that is refrigeration effect, in winter. Your ambient temperatures are lower, your condensing temperatures will be lower. So your ACs will be able to deliver much higher refrigeration effect. So per gram of refrigerant flowing through your evaporator, it will lead to higher enthalpy change. questions, doubts, anything which was not very evident from the cycle? Okay, so now you see why industry wants the pressure enthalpy chart. So they like this pressure enthalpy chart because they can directly get the information of enthalpy straight away from this x-axis. Now let's look at what happens to the specific work. Okay, why specific work is, again, it is per unit mass. We will bring in the information about mass flow rate in the next slide. So what happens with the specific work consumed by the compressor? So if I am reducing the evaporator temperatures, okay, you can see that the specific work increases. And that's quite evident because your pressure ratios are increasing, and hence you expect that you will have to do more work per unit mass. Okay, so this is one thing. Another thing that you can observe is the discharge temperatures over here are also increasing. So let me draw the isotherms. So the isotherms will look like this. So like this. So you see that if you reduce your evaporator temperature, your discharge temperatures are higher because the isotherm which will pass through this will be somewhere here. It looks like supercritical, but this is just a sketch. So you're moving towards right. Okay, so you will have an isotherm which is at a higher temperature passing through this point. Okay, so when you lower down your evaporator temperature, discharge temperature from the compressor goes high. Now let's look at the second case where we have maintained same evaporator temperature but different condensing temperatures. So over here you see that again, yes, someone has a doubt? Okay. So again you see as you increase your condensing temperatures, your delta H, okay, delta H here and delta H here, delta H here, it keeps on increasing. Okay, and similarly your discharge temperatures are also increasing. So the isotherm passing through this could be this one, the isotherm passing through this could be this one. Okay, so similar effect. So either you reduce evaporator temperature or if you increase condensing temperatures, you will have similar effect on the refrigeration effect as well as the specific work of consumption as well as the discharge temperature. So the worst condition that you can operate your AC or a refrigerator is when your ambient temperatures are high or if you set a very low temperature in the evaporator. So these are the worst case scenario. Okay. So any doubts in the previous slide? Because now we will look at the next characteristic and then we'll multiply them. Because ultimately we are interested in the power consumed by the compressor, the refrigeration capacity and not the effect. So we'll multiply the mass flow rate and the previous slides enthalpy difference to get the final product.
Sir?
Yeah.
So in the previous slide, you said we keep the condensing temperature constant and reduce the evaporating temperature.
Yes.
Then again, after reducing the evaporating temperature, you said the discharge temperature increases.
Yes. Yes.
If the discharge temperature increases, doesn't the compressor temperature also increase?
There is nothing called compressor temperature. It is condensing temperature you're talking about.
Yeah, sir. Yeah, sir.
So if you remember from the first class itself, when we were drawing the cycle, I told you the condensing temperature is not equal to the discharge temperature. The condensing temperature is the temperature or the isotherm which passes through the two-phase region. So if I go back to our TS diagram, you see this is the discharge temperature, but we called this as the condensing temperature. This is T, this is S. Okay, so if you have a lower if you have a higher condensing temperature, it means that you shift from here to here. So this is a higher condensing temperature scenario. Okay, but a higher discharge temperature scenario is at the same isobar now. If you go to this condition. Okay, I can further reduce my evaporator temperature and move up. So this is my condensing temperature. Okay, that fixes the condensing pressure.
Okay, sir. Yeah, got it.
So I'll quickly draw the analogous TS diagram. If you are finding it difficult to follow this, I will draw that TS diagram also. Okay, so I am fixing the condensing temperature. So this temperature gets fixed and hence the pressure itself gets fixed. So this is your isobar corresponding to TC. No changes here. What I am changing is the evaporator temperature. So then this is, let's say, the first case. Let me change the color now. This is the second case. Let's change color again. And this is the third case. This curve. Okay, so as I move to lower and lower temperature, you see that I will end up with a higher discharge temperature here. Okay, and this is my expansion process here. This is my expansion process here. This is my expansion process here. So let me again draw it quickly bigger. Clean up this slide. This is your condensing temperature. Okay, it doesn't matter what is your discharge temperature. So this is your discharge temperature, but I don't care about discharge temperature. All I care about is the condensing temperature TC, because that fixes my condensing pressure. This isobar is fixed. Okay, so that is constant. Now what I'm varying is the evaporator temperature. So this is the evaporator temperature. This is the first case. Okay, now let's draw the second case. This is my second case. Let's draw the third case. So it will go down. Continuously go down. Okay, and you see this was my initial discharge temperature. It has moved to this point. It has moved to this point. So discharge temperatures are going high. This is my throttling process. Okay, my refrigeration effect is reducing. Okay, here it is difficult to identify and hence the pressure enthalpy chart. Okay, here because how the slope is there with respect to the throttling process line, that will decide what is the RE. So it is difficult to see the change in RE straight away here. So that's why pressure enthalpy chart was drawn. It becomes easier for us to identify that. Okay, so you can do an exercise by going through the charts and tables, or you can use EES and check.
Yes, sir.
I hope. Yeah.
Yes,
I
sir.
hope that is clear. Yeah. Okay. Okay. So, any other questions? Good that today at least I feel better that there has been a lot of interaction. Any other questions? Okay, so good that all the doubts are clear. Now let's move to the next characteristic curve, that is the mass flow rate. Okay, so mass flow rate. For mass flow rate, it is better to first draw the volumetric efficiency curve, because in the expression for the mass flow rate, you have volumetric efficiency. You, of course, definitely have the volume of displacement volume of the cylinder, but that is going to be fixed because we are looking at one particular compressor. But what you also have is the density of the refrigerant. So into rho evaporator or divided by the specific volume of the refrigerant. Okay. So this evaporator subscript means you have to evaluate the density at the evaporator outlet condition. Okay, not at the evaporator inlet, but at the outlet, because from the evaporator outlet, the refrigerant goes to the compressor. So this rho evaporator or specific volume of the evaporator condition, it is at the exit, at the rate exit. So this also has to be checked. This also has to be checked. These things are easy to understand. Number of cylinders, if you increase, you will get more mass flow rate. If you increase the RPS of the compressor, you will get higher flow rate. So what we are now looking at is just the effect of operating condition. So if I just look at the volumetric efficiency will go from 0 to 1. Okay, and in the first in this slide you see Tc is constant. That is, the condensing temperature is maintained constant. I am varying the evaporator temperature. So if I go to lower evaporator temperatures, then my pressure ratio will increase. Okay, so Rp is equal to Pc over Pe. This Tc is fixed, hence Pc is fixed. So that isobar is fixed. So all I am changing is Te, which will vary the Te. Now if I reduce Te, I will have lower and lower evaporator pressures, which means that my Rp will continue to increase. So at lower evaporator temperatures, you will have higher Rp. Okay, and at higher evaporator temperatures, you will have lower Rp. Okay, and the best case scenario would be where your evaporator temperature is just equal to your condensing temperature. That will give rise to a pressure ratio of 1. So that is the entire range which we are looking at. So Te will go from Tc all the way till one particular value where you get the Rp max. So you have to first get the Rp max from the previous slide expression, and whatever it tells you, that is the maximum pressure ratio you can go up to, and that will give you the what is the minimum evaporator temperature. Okay, so this is where it will go to 0. This is where it will go to 1. So this is your volumetric efficiency curve. Okay, now what we need to do is we have to multiply this curve with the density of the refrigerant at the evaporator exit. So this will be equals to, if I use the EES, so it will be density, whatever the refrigerant is, at P equals to P evap and X equals to 1. Okay, so if I reduce the P evaporator, what will happen to the density? Any idea? If I reduce the evaporator pressure, what will happen to the density of the refrigerant at the exit of the evaporator? Will the density reduce, increase? Let's say my evaporator is operating at 5 bar and I reduce the evaporator pressure to 3 bar, then 2 bar, then 1 bar. What will happen to the density?
It should reduce.
It will reduce. Okay, so what will happen is if you reduce your evaporator temperatures, then so that will reduce the evaporator pressure and hence the density. Already your volumetric efficiencies are reducing. Okay, densities will also reduce. So you get a double whammy here. So your mass flow rate will significantly reduce. Okay, so this is reducing from the curve itself, we can see, because your RP across the compressor is increasing. So higher RP, lower is the volumetric efficiency. So one negative effect. The next negative effect is my densities are also reducing if I am reducing the evaporator temperature. So the product of these two will be even smaller value. So at lower evaporator temperatures, the mass flow rate delivered by your compressor is extremely low. And hence you will see that if you have a refrigeration system which is, let's say, 1 ton, which provides 1 ton for air conditioning application, and another compressor which delivers 1 ton capacity, let's say for a cold storage unit. Okay, this is for AC and this is for a cold storage unit, where the temperatures, let's say, are to be maintained at -10, -20 for meat storage. The compressor for the 1 ton cold storage will be significantly larger than the 1 ton AC because it is maintaining a lower temperature and yet it has to deliver 1 ton capacity. Okay, so it has to deliver sufficient amount of mass flow rate, sufficient amount of refrigeration effect, so that the product of those two will give you the 1 ton. So at such low temperature, that poor compressor will not be able to suck in a lot of refrigerant because of poor volumetric efficiency and poor densities. So we'll have to provide a much larger compressor there. Even though the capacity for that system is also 1 ton and the AC which we are using at your home is also for 1 ton. But yet your AC, residential AC 1 ton compressor will be much smaller because the densities are higher and the volumetric efficiencies are higher, because you are not operating across such large pressure ratios. Doubts, questions? Okay. So this right side figure is the same thing which I was just now discussing about the refrigeration capacity. Okay, so for understanding refrigeration capacity, let's first quickly draw the refrigeration effect. So as I reduce the TE, refrigeration effect reduces. This is what we saw from the previous slide. Okay, but the mass flow rate is also reducing. So now the product of mass flow rate into this refrigeration effect is what we get. So these are all just hand-drawn curves. So if you want to get the correct curve, you will have to write an EES program there and vary the conditions, you will get the proper curve. Okay, so in turn, if you look at the refrigeration capacity, you have a triple effect. First, m dot itself has the negative effect of volumetric efficiency and densities. Then you also have a negative impact of the reducing refrigeration effect. So when it gets multiplied to the m dot, you get the refrigeration capacity. So that's why I think few AC manufacturers are trying to educate us that do not reduce your set point temperature to very low values. Okay, so because it will, so your 1 ton AC may not be operating at 1 ton capacity now. If you try to maintain very low temperatures, unrealistically low temperatures with your AC. Okay, then you cannot go and complain to the manufacturer that oh, 1 ton capacity to nahi hai iska. Okay, so this curve is true for all refrigeration systems. So if it is rated at a particular operating condition as 1 ton, if you lower the evaporator temperature, the capacities will be reduced. Okay, so all the time we are maintaining TC constant. Difficult to get the effect of two things happening simultaneously. So right now we are maintaining TC constant. Okay. Any questions in the previous slide? So right now, what I understand is most of the manufacturers are trying to educate us that in order to reduce the power consumption and help your AC operate at its rated capacities and all, it is better to provide a set point of around 24, 25, okay, not lower than 24. You will see there is a label that 24 is the best operating condition, because 24 will give you a decent amount of thermal comfort and it will not reduce the capacities and increase the power consumption of the system. Okay, and they'll also give some thumb rules also. For every 1 degree reduction in temperature from 24, you will consume this much of additional power. Okay, so those things are also right now given as a sticker in your indoor unit. These are all the outcome of what we are right now discussing and trying to educate a layman. Okay, so we have seen the effect on the refrigeration capacity. Drastically it will reduce if you reduce your evaporator temperatures. Now let's see what happens to the compressor power consumption. Okay, so compressor power consumption, if you look at the delta H compressor, okay, so delta H compressor is nothing but the specific work. Specific work. So specific work, if you reduce your evaporator temperature, that kept on increasing. Okay, and if you increase your evaporator temperature, it will reduce. So this is the limiting case where TE equals to TC. RP was equal to 1. This is your other limiting case where T equals to TE minimum, that corresponds to RP max. Okay, you will not have any flow rate beyond this. Compressor will not deliver anything. Okay, so this is a reducing curve. Whereas if I, so very high power consumption at RP max, very low power consumption here. But if I look at the mass flow rate curve, it delivers very high mass flow rate at RP equals to 1. Okay, volumetric efficiencies are good, your densities are good. Okay, so it delivers very high mass flow rate and it delivers zero mass flow rate here. So on one hand, you will have power consumption going to zero here, specific power consumption. So specific work going to zero here, whereas mass flow rate is very high. In the other limiting case, you will have mass flow rate 0, but your specific work is very high. When you take the product of these two, you will get something of this nature. Okay, parabolic curve. So this is your power consumption, W dot. This is your W dot per unit mass, and this is your M dot. Okay, so it will peak at some value and then it will start reducing. So on this side of the curve, you have low specific work consumption but very high mass flow rates. On this side of the curve, you have very high specific work consumption but very low mass flow rates. So that's why you have the product peaking at a particular value. Okay, now this is an issue for most of the refrigerators or cold storage units. Now, when you operate your cold storage units or refrigerators, you operate very close to your RP max. So now somewhere here. Because the expected temperature in the evaporators are very low, -20, -30 of that nature. Now, when you start your refrigerator or a cold storage unit for the first time, it will start from T equals to Tc. Okay, and your compressor demand will initially rise. Okay, and it will pass through this peak and then it will drop. So it will pass through this entire curve. So your motor should be designed or capable enough to deliver this peak power. Okay, this peak power is different from the induction motor demand. Okay, so this is from the compressor side. We are not looking at the motor side right now. Okay, so your induction motors require a starting torque and that requires an initial peak current. That is not what this is. Okay, so that is from the electrical point of view. This we are discussing from the thermodynamic point of view or mechanical side. So your compressor will demand a lot of torque because of this increase in work of or increase in power input. So if you do not provide a sufficiently large motor, then you will have motor overloading. Okay, your compressor will seize. So that's why you will see your domestic refrigerator, especially the because we have all those hermetically sealed compressors, so you're not able to see that if this is the size of the entire casing, you will have the compressor displacement volume only this much. And the rest of the thing is, of course, you have your huge motor winding and shaft and lubricating oil kept in the crankcase. Okay, so the rest of the space is predominantly occupied by the motor itself. So you would wonder that why do we need such a large motor for such a tiny compressor? It is because of this power peak. Okay, and hence it is advisable to not switch off your refrigerators if you're not going away from your home for a very long time. Let it operate. Okay, so don't make your motor go through this power peak again and again. Whereas fortunately for ACs, we normally operate and in this region. Okay, so it is not as if we'll go through a peak and then the power consumption will drop. Suppose we do not have an understanding of this entire characteristic and I ask you what is the motor size required for your domestic refrigerator. So you will end up with an answer which is this, because you will only carry out this calculation at one point. Okay. So you will not realize that there are other points through which it will pass. Every time when you turn off your system completely, allow it to go back to the ambient temperature and then turn it on. So if this happens again and again, your motor will go through this peak. Whereas in your ACs, you will typically operate somewhere here. Okay. So that's why they will say that if you go to lower and lower evaporator temperatures, the manufacturer will say you will consume more work. Because you are on this side of the curve. Whereas in case of a domestic refrigerator, further lowering the temperature will lead to lower power consumption. But then it will also produce lower capacity. Okay, so we are right now not discussing about COP, we are just looking at these two numbers separately. So from here, if you further reduce your evaporator temperature, you will reach here. Your demand on the system will further reduce. But yet the motor will be oversized because of this power peak. Okay, but now with all this inverter control, okay, so this discussion is limited to the fixed speed compressors. Now with all our understanding of the electronics part, and we can modify the RPM of the motor. Okay, so if we have all these controls, then we can reduce the power peak. So we do not start the compressor. So this is, I'm talking about the domestic refrigerators only. we do not start the compressor at the full speed. We start it at a lower RPM. Okay, so lower RPM means two things. Your demand on the motor will be low, but your refrigeration capacities will also be low. So you will cool slowly, demanding less power from the motor. Okay, and once you are through this power peak, maybe when you go to this, then you start increasing your RPM. This is one way of controlling the peak load. Okay, so in this fashion, you can have a smaller motor connected to the compressor. Or in many cases, in large cold storage systems, we will have multiple cylinder. Okay, it will not be a single cylinder compressor, it will be 2-4 cylinder compressor. In such scenarios, we can also cut off 1 or 2 cylinders. Okay, till a particular temperature is attained. Again, the demand is less on the motor and hence the capacities will also be poor. So you will take more time to pull down the temperature. Okay, but then you are saving on the capital investment of a larger motor. And that larger motor is just there for that initial peak period. That's it. Never ever will you demand that amount of power in case you are far away from this peak on the left side. Yeah. So the entire characteristic needs to be drawn. When we perform calculation in a classroom environment, we ask you for one operating condition. But when you go and design systems for a practical application, you need to see the bigger picture. Okay, so electronically, I can control the RPS, and mechanically, I can cut off few cylinders in case it is a multi-cylinder compressor. Okay, if it is a fixed speed compressor, single cylinder, then I will have to go for a larger motor. Any questions here? So when you see in an AC, the manufacturer tells that if you go to lower evaporator temperature, it will increase the power demand on the compressor. The same will not be true for the domestic refrigerator because you are on the left side of the peak. But one thing is for sure, if you go to lower evaporator temperatures, your capacities would be drastically reducing. Okay, so there is no peak in there. RC continuously drops, as we have seen here. It continuously drops. Okay, so this is RC and this is RE. Any questions from previous 1 or 2 slides? Okay. So all the discussions till now were restricted to a constant condensing temperature, but variable evaporator temperature. Now let's move to the second case where we will maintain the same evaporator temperature, but change the condensing temperature. Okay. So the first plot is for the volumetric efficiency and mass flow rate of refrigerant delivered by the compressor. Okay, so the expression over here will directly tell you that it doesn't have a dependency of rho condenser. It has the dependency of condensing pressure in form of the pressure ratio. Okay, so RP is equals to PC over P. I'm sure here. Okay. So PC over PE equals to RP. So PE is constant because PE is constant. Huh? Temperature is constant, pressure is constant. So condensing temperature is varying and hence condensing pressure is varying. So as you increase the condensing temperature and hence the pressure, your volumetric efficiencies will go down. Okay, but if you see what is the density multiplied by the volumetric efficiency is the rho evaporator, which is constant. So your mass flow rate curve and your volumetric efficiency curve will be parallel to each other. Okay, whatever trend you have in terms of volumetric efficiency, you will have the same trend in terms of mass flow rate delivered by the compressor. Okay, because you have a single effect. Now, if you go to the refrigeration effect and refrigeration capacity, so as you increase the condensing temperature, we saw that the refrigeration effect decreased. Okay, and your mass flow rate is also decreasing. And okay, so don't take this as a straight line perfectly. So you will have the product. So both are decreasing. Okay, in the first case, in the case where we were changing TE, we had three effects. One was rho evaporator changing, we had volumetric efficiency changing, and we had the RE. Okay, RE changing. Okay, so all these three got multiplied to form the RC. Whereas over here, this effect is not there. Okay, so you have only the volumetric efficiency which is reducing and the refrigeration effect. You have only two effects which is changing the RC. Okay, you will see if you actually do some example problem, you will see that density is a very dominating factor. Okay, so if you follow the same logic and do the same exercise now for the specific work consumed by the compressor and then the mass flow rate delivered by the compressor and then take the product and get the power input to the compressor, you will see again over here also you have a curve of this nature which peaks and then comes down. Okay, so as you increase the condensing temperature. Yeah, but most of the time you will see this peak happens well beyond 60 degree or close to 60 degree, 58, 60 degree. So for most of the practical systems, you will be operating in this range, which is a good thing. Okay, so fortunately, you will see for most refrigerant, you will see the peak happening at unrealistically very high condensing temperatures. So you will most of the time operate here. But you have similar trend. Theoretically, you will have similar trend. So here I forgot to add the mass flow rate curve. So mass flow rate curve was somewhat like this. Doesn't go to 0 here. So RP max is not drawn here. So mass flow rate, and this is the delta H compression, means this is the specific work. Okay, and this parabolic nature curve is the power input to the compressor. Okay, so let's quickly do one example problem so that we can see all these characteristics. So you have refrigerant R134A, gamma is given. Is used for a refrigeration system with 4-cylinder compressor, each having 40 cc displacement volume and operating at 3000 RPM. The design evaporator temperature is -10 degrees C, whereas the condensing temperature is 45. Assuming 5% clearance ratio, which is very high. and isentropic compression and re-expansion process. To answer the following, what is the design refrigeration capacity and what is the compressor work? And if a 4.5 kilowatt motor is coupled to the above compressor, will the motor overload happen if the temperature rises to 0 degrees C, while the condensing temperature remains at 45 degrees C? Basically, indirectly, we are looking at if we are on the left hand side of the peak or on the right hand side of the peak. Okay. So we can quickly write the code and check. And what are the conditions given? N cylinder is equals to 4, RPS equals to this. Okay, V displacement in meter cube, how much? 40 cc in meter cube, how much?
14 to 25 minus 6.
And then epsilon, let's call this E, is 5. And C is 45, T is minus 10. Okay, so let's get the enthalpy difference across the, what we have to first find out is the refrigeration capacity and the compressor work. Let's get the volumetric efficiency. What is the expression? Yes, 1.163. Condensing pressure. Okay. T equals to C. And let's get the evaporator pressure. So this will give me the pressure ratio. What is the expression for volumetric efficiency? Let's go back and quickly write the expression here. One neta equals to 1 minus E comma minus 1. Okay. Okay, let's check quickly neta. We need to get is mass flow rate. So mass flow rate will be neta times displacement volume times density. Density at T evaporator x equals to 1. So this is the density of the refrigerant at the exit of the evaporator multiplied by what else? RPS times N cylinder. And so before proceeding, I will show you how to draw a table. I want to draw a table in ES. So let's assume that I want to maintain TC constant. I want to vary T evaporator. Okay, so right now we are just getting 1 point on that curve. So what we need to do is create table, new parametric table. And what are the parameters which you want to vary and what is the output? These things have to be specified. So I want to vary the T evaporator. And I also want to, check the mass flow rate M. Okay, so let's say I want to see this curve, how M varies with T evaporator. So these two are the parameters now. So that's okay. We will get a table here. And then you want to vary the T evaporator. So click on right click and then get this alter variables. Let's say I want to go from -20 at an increment of 5 degrees C and 10 rows are there. So it will create this. Now it will solve this code and fill up the mass flow rate column. But then you have already specified the evaporator temperature over here. So you have to comment out this TE over here. And then go to table, go to calculate and go to solve table. That's okay. You will see the variation of mass flow rate with evaporator temperature. Now, if you want to plot this, go to plot, new plot, XY plot. So x-axis is TE, y-axis is M, the two variables. This is how it varies. So this is how you can create the plots and tables in ES. Okay, so let's now check the enthalpies because we ultimately need the power consumed by the compressor and the refrigeration capacity. Let's call the enthalpy at the exit of the evaporator as H1. Enthalpy, fluid name T equals to TE, X equals to 1. Okay, and we also need to get the entropy because we will assume right now since isentropic efficiency is 1, so we'll get the isentropic compression work done. So T equals to TE, X equals to. Okay, H2 will be equals to enthalpy equals to PC because I do not know the discharge temperature from the compressor. So I will make use of the condensing pressure and entropy as the two properties to get the enthalpy. Okay, so S equals to S1 ensures that this is an isentropic compressor. P equals to PC because we already know what is PC. So based on this, we'll get the enthalpy at the exit of the compressor. This was the enthalpy at the inlet of the compressor, which is equal to the exit of the evaporator. And for refrigeration capacity, I will also need the enthalpy at the exit of the condenser. So nothing about subcooling is given, so we'll assume it to be saturated condition. Okay, so all the requisite enthalpies we have written. Now we just need to write what is RC. So RC will be equals to M times H1 minus H3. And work consumed will be M times H2 minus H1. If you want to see the COPs also, you can write. Okay, so this has been created and then you can uncomment this. We'll get the refrigeration capacity for the evaporator temperature of -10. So this is just a point. Okay, and what is asked is, go to the question. What is the design capacity and compressor work? Okay, so we are getting something different. Made a mistake somewhere. 4 cylinders. 4 cylinders. Refrigerant is this. And okay, let's check the ambiguities. Let's see this code. Maybe I think we have made a mistake in writing the expression for volumetric efficiency. No, I think it's all fine. Maybe my answer that I have written in the slide could be wrong. So RP looks fine. So this one point is not very interesting. Let's look at the entire table now. So we go back to the table and we can plot now COP and refrigeration capacity and work of input to the compressor. Parametric table. We want T evaporator. Where is T evaporator? T evaporator. Then we want N. We want RC work. Anything else? No. One of it. The values minus. Now, if there is a mistake, we'll be able to catch. No, trend looks fine. Okay, now we go to plot. XY plot. Let's look at the refrigeration capacity. Okay, let's create the work consumed by the compressor. Okay, so you see it is peaking at somewhere close to 12, 13, maybe 15 degrees C. Okay, so it is peaking somewhere here. So if our operating condition is -10 and if I increase the temperature from -10 to 0, your power demand by the compressor will rise. So your power consumed is going to rise. So that's why many a times the domestic refrigerators and cold storage units, they may even have a cutoff in terms of a higher evaporator temperature. So in case you keep your say your refrigerator open for a long time or your cold storage units are open for a long time and the evaporator temperature goes very high quickly, so they may cut off the compressor. Okay, so such instrumentations to safeguard the sudden overload on your motor are also provided. Okay, so beware of keeping your deep freezer segment open for long time. Okay, so hopefully now you believe the plots that I have shown. So this is the mass flow rate versus TE. This was the RC versus TE. You see at 10 degree, if your refrigeration capacity is 20 kilowatt, at 0 degree, it is close to 12. At minus 10, it is maybe about 5. Okay, so it is very sensitive. And this is the work of compression. Okay, and one thing which is remaining is the COP. Okay, I forgot to add COP here. We just solve table number 2 now. What happened? Oh, I didn't add. So you can see from the trend itself that COP is continuously decreasing as you reduce your evaporator temperature. Okay, so this is where I'll stop the recording.